Have you ever wondered what actually holds atoms together? I mean, it's this invisible force that builds literally everything around us, from the water we drink to the air we breathe. Well, to get it, we need to look at this fundamental battle that's always happening on the atomic level. Because you see, when two atoms come together to form a chemical bond, it's not always this peaceful, cooperative thing. Nope. A lot of the time, it's a competition, a battle for one of the most important particles in the universe, the electron. Honestly, the best way to think about it is like an atomic tug-of-war. You've got each atom pulling on the electrons in the bond, and the outcome of this constant pulling match, it determines the entire nature of the chemical bond itself. Okay, so if it's a tug-of-war, how do we measure an atom's strength? How do we know who's going to win? Well, chemists have a specific term for this pulling power, and it is the absolute key to understanding how all of this works. And that term is electronegativity. Now, it sounds a little complicated, but the concept is actually super simple. The higher an atom's electronegativity, the stronger its pull on an electron. It's basically a number that tells you its pulling power. And you can see just how different this pulling power can be. I mean, look at fluorine at the top. It is the undisputed heavyweight champion of the periodic table with a value of 4.10. Then you look way down at the bottom, and you've got atoms like sodium with a much, much weaker pull. It's this huge range that creates all the amazing variety in chemical bonds. So what happens when you pit a heavyweight like fluorine against a real lightweight like sodium? Well, as you can probably guess, this massive difference in strength leads to a very, very clear outcome in our atomic tug-of-war. On one side, you get what we call an ionic bond. This isn't a match, it's a total victory. The difference in strength is so huge that the stronger atom just completely rips the electron away from the weaker one. A perfect example is sodium chloride. Yep, regular table salt. But on the other side, you can have a covalent bond. This is more like a partnership, where two atoms with pretty similar strength decide to just share the electrons. And this shows you the direct consequence of winning that tug of war. The stronger atom, the one with the higher electronegativity, takes the electron and, because electrons are negative, it gets a negative charge. It becomes a negative ion, and the loser, it's left with a positive charge. But, okay, this is where it gets a little more subtle, and honestly, a lot more interesting. We just talked about sharing in covalent bonds, but that brings up a really critical question. I mean, is that sharing always a perfect 50-50 split? What happens when one of the sharers is still just a little bit stronger than the other? Well, that leads us right to the polar covalent bond. This is the crucial middle ground between a total knockout and a perfect tie. So it's still a covalent bond, the electrons are being shared, but that sharing is totally lopsided. Let's go back to our tug-of-war analogy. You know that little flag in the middle of the rope? Well, in a polar bond, that flag isn't in the middle anymore. It's pulled closer to the stronger team. The shared electrons are doing the exact same thing. They're spending way more time hanging out around the more electronegative atom. And this uneven sharing creates a fascinating result. The stronger atom, since it has the electrons closer to it more often, gets what we call a partially negative charge. And the weaker atom, with its electrons being pulled away, is left with a partially positive charge. Now, these aren't the full-blown charges you see in an ionic bond, but their consequences are absolutely massive. So this whole idea of partial charges reveals a really key insight. Chemical bonding isn't just two separate boxes, ionic and covalent. It's actually a smooth, continuous spectrum. And the rule that governs this entire spectrum is beautifully simple. The greater the difference in electronegativity between two atoms, the more polar or the more lopsided that bond becomes. Simple as that. Let's see this in action. This chart shows what happens when hydrogen bonds with a few different atoms. With nitrogen, the difference in their pulling power is 0.87. But with oxygen, it jumps to 1.30. And with our champion, fluorine, it's a whopping 1.90. The trend is crystal clear. As that difference goes up, the polarity of the bond gets stronger and stronger. So here it is, the whole picture. When the difference in strength is tiny, we call it a nonpolar covalent bond. That's a nearly perfect equal share. As that difference grows, it becomes a polar covalent bond, our unequal share. And when that difference becomes huge, sharing stops altogether, the electron gets transferred completely, and we call it an ionic bond. It's all just one sliding scale. So let's put it all together. What do you need to remember? First, electronegativity is just an atom's pulling power. Second, this constant power struggle determines how electrons are shared. Third, unequal sharing creates those super important polar bonds with partial charges. And finally, chemical bonding isn't just two boxes, it's a whole spectrum. So why does any of this matter? Well, that tiny little partial negative charge on oxygen and partial positive charge on hydrogen in a water molecule is what makes them stick together. It's the reason water is a liquid at room temperature, a property that makes life on Earth even possible. Think about that. This tiny imbalance in a game of atomic tug of war literally shaped our entire world. Makes you wonder, what else does it explain?